Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Juan Luis Rizos with us today. Hello, Juan.
Hello, nice to meet you in person, Frank. Thank you
Nice
for
to meet you
inviting
in
me.
2D, Juan. On this
Yes.
January 24th of 2025 as we record this. Let's see, Juan, what's your geolocation? Where are you located?
Well, I am currently in Cordoba, in southern Spain,
Cool.
at home. I am Spanish and I currently work at the Instituto of Astrofísica of Andalucía.
Very nice.
However, the work that we are presenting today, I want to say that it began in 2021 at the University of Maryland under the supervision of Jessica Sunshine, but I continued it here in Spain after coming back in 2023.
Okay, very cool. Very cool. Very nice. Let's see. It is January in Spain, so does that part of Spain get snow? Does it get cold?
No, it is winter here, but in the south it is not very cold. The minimum temperature can reach 0 degrees Celsius. It
Yeah.
is nothing compared to New York or Washington, D.C.
Right, right. So I'm in Phoenix, and I'm in the desert, and we're definitely in our winter mode. So yeah, we will go down around maybe 0 in the night, but it'll warm
The
up
same.
very pleasant in the daytime. So very cool. That is an awesome t-shirt you got on there, Juan. What is that? Extremo Duro.
It is Extremoduro. It is one very nice rock band here in Spain. It is the first album, I don't remember the number, called Iros Todos a Tomar por Culo. It is very nice. I
Yeah,
recommend.
very cool. Very nice. Are you in the band?
No, I would like. I would like.
You never know.
I play the bass guitar, but not in a famous band,
Very good.
unfortunately.
Very cool. And Juan, what do you like to do for research?
Well, I am a planetary scientist, and in my career, I have worked in the small bodies field, studying asteroids, comets, centaurs, TNOs, from different approaches, from ground-based observations to stellar occultations, and
Cool.
also space missions like OSIRIS-REx and DART. And Ceres is one of these small bodies, or almost a small body, because it is somewhere between a large asteroid and a dwarf planet.
Yep.
And this is some of the reason why it is so interesting because it might represent an intermediate object.
Absolutely. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. New candidate
Okay.
for organic rich regions on Ceres. And Juan, take us away.
Okay, first I want to thank the co-author that participated in this paper, mainly Jessica and Terry for their nice help. And I'm going to tell the story. In 2017, scientists from NASA's Dawn mission,
Okay.
which first visited the asteroid Vesta and then the dwarf planet Ceres, discovered organics in a crater called Ernutet. These were identified by a spectral feature in the infrared at 3.4 microns,
Uh-huh.
indicative of their presence, but we wanted to know more. How are they distributed? What does this distribution means?
Right.
Are they only found in Ernutet? Or why? No.
Mhm.
So many interesting questions, which led us to study these organics from every possible perspective.
Cool.
And as a result, we identify this new region that might contain organics, which is the main outcome of this work.
Very nice.
And among them stands one, the most interesting but I'm not going to do an spoiler. No? So let's see it later.
Okay.
Let's start if you want in presenting the instrument. This space mission have several instruments, but we have been using the framing camera too, which is a camera in the visible,
Yep.
and the infrared spectrometer.
Okay.
Okay, and we know that on the surface is composed by opaque material, phyllosilicates, carbonates, salt, water ice, monated minerals. But the most interesting is that we found organics.
Ah,
As I told you, it can be identified in the infrared at the 3.4 absorption band, but
oh,
also in the visible, you can see a reddening of the spectral slope.
Mm,
So we use this proxy in our algorithm to identify or search for more organics.
I'm with you.
Okay, so if we go to figure one, you can
Yeah.
see there an example of which is an organic rich area in red. This is how it looks.
Yeah.
And in gray, a non-organic rich area.
Okay.
The organic rich area is very clear. You can see this 3.4 absorption band, but it's interesting, and I have to say here that also in the gray spectrum, you can see a shallow 3.4 absorption band.
Yeah.
And
Mhm. Yes.
it complicates our life a lot because the presence of carbonates everywhere on the surface. Okay,
Okay.
so if we go to the figure two, there
Okay.
I just plot the carbonates that are supposed to be on the surface of Ceres.
Very nice. Okay.
And people will see that, for example, calcite, dolomite, all of them, they have the 3.4 absorption. So
Yeah.
when you have carbonates and you don't have a clear signal of organics, it's very complicated to say something. And that's the reason why we have to use all the different perspectives that were
Okay.
possible to analyze this. And that's the reason why we are talking always, even in the title, about candidates, just to be honest, because these carbonates, yes, carbonates are complicating our lives.
Yes.
And there was a debate about the origin of these organics. On the one hand, people thought that maybe they were just exogenous material that were delivered via impact of organic rich asteroid or comets. No?
Right.
And the fact that only in one place it is clear that there are organics support this hypothesis, just one location. But there are also people that thought that they are endogenous, that they fall inside of Ceres. So this was
Oh, yeah.
our goal also
Okay.
to shed some light, no, about this discussion.
Hmm.
And what we did was using an innovative approach, which is called the spectral mixture analysis, which is
Okay.
in the section two. Okay.
Mhm.
And just to have a global idea about this algorithm, the first thing that we need to do is to identify the basic spectral units and members, we call them members, that compose the surface.
Okay.
Okay.
I'm with you.
And this is what, sorry?
I'm with you. Okay.
Okay, sorry, yes.
I'm following.
And this is what we do in the equation one, the
Yes.
system of equations.
Yes.
We have one equation for each color filter of the framing camera.
Hmm.
We use principal component analysis, clustering algorithm, different approaches until get the basic members, the
Okay.
fraction abundance that is represented with the letter F.
Yes.
For doing this part, we constrain this result, this least square, so that the sum of all the abundances is one, no,
Okay.
100%. But however, we didn't constrain the abundances of each member between 0 and 1.
Ooh. Okay.
Instead, we allow to have negative values and even super positive. Why? Because these wrong solutions help you to know what is the right path to say, no, this
Okay.
choice of in member
Okay.
is not the correct one. I need to remove
Okay.
this. It is very manual. It is not an algorithm that you just press a button and you
Yeah.
have the result,
Bang.
unfortunately. Yes. So that's the first thing. And
Okay.
the second thing, which is the most interesting from my point of view, is that we can get what we call an extrapolated data set,
Yes.
which is a new map with the spatial resolution of the framing camera, but the spectral resolution of the spectrometer.
Very cool.
So that's the innovative thing. And this is what we are just doing in the second equation.
Very
It's the
cool.
same equation, in that
Mhm.
case with the infrared.
There we
We
go.
already know the abundances. And now what we want to know is the intrinsic behavior, intrinsic reflectance of each one of these members that we call hyperspectral members. Okay,
Mm-hmm.
so that's the technical approach.
Got it.
If people want to know more, can read the paper or just can go, for example, to Chick and Sunshine 2020 because they use the same approach but on Vista and they have very nice results also. This is referenced in the text.
Mm-hmm.
So
Give a
it's
shout out.
just my, yes.
Mm-hmm.
And let's go, if you want, to the results.
Sure.
I'm going to show you some interesting results. For example, if we go to the figure 3, I
Sure.
am showing there an RGB map.
Ooh.
It is a map in which I am plotting each end member that we have identified in a global scene where the organics are.
Shade.
This
Okay.
yellow arrow is pointing toward the Ernutet crater.
Mm-hmm.
All these red spots that you can see are the organic member,
Cool.
and it's a very visual way to know what's going on this region. And when we saw this map, we said, "Oof, okay, it's very interesting, but we can even go further and use this approach to identify new regions with organics."
Yes. Yes.
But our first purpose was to analyze the distribution of the organics in Ernute with this new superpower of the extrapolated dataset. And this is what you can see in figure 4.
Okay.
In figure 4, we are showing the abundance map of
Ooh,
the
nice.
member of the organics,
Mhm.
but at a resolution of 35 meter per pixel,
Wow.
which is very,
Very
very
cool.
nice.
Very
Yes,
nice. Yeah, beautiful.
yes. And we see that this organic material is spread out in granular distribution
Okay.
with highly localized areas showing high abundances.
Yes.
We didn't see the expected morphological characteristic following an impact, no, because this material is inside the crater, in the walls of the crater,
Got it.
outside the crater,
Yeah,
is
yeah.
everywhere.
Okay.
And the distribution of the brightest spots suggests a circular pattern starting, if you go to the next figure, figure 5,
Yeah.
you
Oh,
will
there
see
we go.
some
There we go.
stars with colors.
Yeah. Mm-hmm.
Yeah, so starting from the ring of the Nutter, the blue star, to the farthest region, the red star,
Okay.
you can see like a circular pattern.
Yes. Uh-huh. Half a
And
mm-hmm.
we note that these organics are just between an old crater, which is represented with this yellow dash circle
Yes.
outside of Ernutet. This is an old crater, and they are there. So we said, wow, what is this? It is telling us something. Maybe an ancient impact play a significant role in enhancing this upwelling mechanism.
Okay.
No? So it is just one hypothesis that we note in the paper.
Nice. Very
And then we said, okay, let's try to find more organics. People said, we have reviewed everything, every pixel, there is no more organics. And we said, okay, let's try, why not?
Why
It is
not?
for free. So we
Exactly.
did it, yes, and we found another 11 regions
Very
that
cool.
this algorithm show this strange or different behavior in the visible, which is indicated, or they are representing the figure 6.
Yes. Okay. Figure 5, figure 6. We're gonna look
There
at
we have the 11
beautiful.
regions
Very cool.
with more candidates
Yes.
according to the visible behavior, the visible spectra.
Okay.
And just a little below in the figure 7, you can see the RGB maps of each one of these candidates.
Okay, let me go there, and then figure 7 is a zoom on each of those.
There.
Okay.
So all these red spots are candidates. They have an redder spectrum in the visible,
Yes.
which is associated to the behavior of the organics. And for example, In the figure 7 in V, you can see in the south of this crater a very clear spot, or in D,
Bang,
we have a spot
bang.
just in the wall, just outside the wall. So
Right.
it is not something random. It is very clear that there is something that is going on there. Okay.
Yes.
So the next
Bang.
step was, okay, let's use the view spectrograph data
Okay.
to go there to see if we can see this 3.4 absorption band.
Exactly.
But unfortunately, but as I told you, it is with the carbonates and it's very hard to say anything clear.
Okay.
So we
Caveat
just
on.
can't talk. Yes, we just can't talk about candidates. However, there was a very interesting area, which is the spot, it is the 12th in the figure 6
I'm
in
sorry.
red.
Uh-huh. Figure six, back to
Yes,
figure six. Mm-hmm.
figure
Yes.
6 in red,
This
it
one
is
right here as well. Yep.
the most interesting
Mm-hmm. It's the biggest one.
because it is located between the Urbara and Jalodi basins. And in
Yes.
that case, it
Yes.
does show the 3.4 absorption band very, very, very clear.
Cool.
So we said, wow, we have something here.
Yeah.
But for example, going back again to the candidates, the problem is that the organics, when they are on the surface, because the irradiation of the solar irradiation, the ultraviolet, destroy the organics.
Right.
So there are several papers showing that there is a progressive suppression of the 3.4 absorption one because this solar interaction.
Radiation. Yep.
So it is possible that these organics are present. They have this characteristic absorption band, but they are at lower concentration because of this reason, and they may not be detectable at the spatial scale of the Vero observation.
Fair enough.
So it is bad, but it's a good point to have a good reason for a next space mission,
Yes.
maybe a sample return mission on Ceres. Who knows?
Nice. Another one is
Yes.
yes.
So we said, okay, let's go to focus on this Jalode area.
Yes.
And this is what you can see in figure, for example, in figure 8.
Okay.
We just did this, again, RGB map with just focus on this region with
Yes.
the abundances of each
Uh-huh.
member.
Uh-huh.
We are including figure 8A in the top, the clear filter image, just to show people the region that we are studying, the context around.
Yes.
This red arrow is indicating another candidate that other people found 2 years ago,
Okay.
just in the center of the Urbana Basin. And another interesting thing is that this region, it is not smooth. You can see that it has suffered a geological activity in the past. You can see these
Yeah.
catinas, there are
Yeah.
channels, groove, stress, and it is very important for what I'm going to say you later. Okay.
Cool. Good. Okay. That's cool.
So the first thing that we did was just representing in figure 9 the spectral behavior in the visible of these candidates, these bracket spots that we call VS1, VS2, and VS3 in this
Oh,
Jarode basin. And we can see that the organics there are in red, the series background is in gray, and our candidates are in the middle. It is this green,
then
blue, and
yeah.
orange spectra. So they are redder than the average, but not so red than the organics. So it can be interpreted as if they are organics, they don't have the same concentration. So
Fair.
it is an explanation.
BS1, BS2, BS3. You can see the red dots in there. There's our organics in there. And then there's the
Mm,
spectra. Okay, I'm with you. Uh-huh. Uh-huh.
Yes. Another thing that we did was trying to explore these spots with the maximum resolution, and this is what you can find in figure 10. It
Okay.
is just a zooming in each one of these bright spots in which we found these strong candidates
Oh, beautiful.
to
Okay.
have organics.
Yeah, fun.
And you can see that they are, for example, the first one, it is just in the middle of a small crater, but not just in the crater. The second one has a very strange shape because it is elongated. It is
Yeah.
something, what does it tell us, no? or the second one is also just in the middle of these small craters.
Yeah.
But what is clear is that this strong absorption band is there, and this is what you will see in figure 11. In figure 11, we are representing the weird infrared spectra of each one of these bright spots.
Yes, it's 1, 2, 3.
And in all of them, for different samples, you can see the 3.4 absorption band. It is very,
Yeah.
very clear.
Very clear.
However, if we see that at 4 microns, we also have absorption band, and it is because the presence of the carbonates. So we have carbonates there.
As well, right.
So we have carbonates. However, it is not strain. Even in the NUTED, when we have the confirmation, you can see carbonates. And which is even more interesting is that where you have more carbonates, you have more organic. There is a clear connection between the presence of carbonates and the organics in some parts on NUTED. So we need to know, and this is also for the future, what is the relationship between the carbonates and the organics?
Yes.
Hard to say, because another thing that I didn't say is that we don't know the exact nature of these organics. We know that they are aliphatics, but there are thousands of different aliphatic organics.
Yeah.
Which one is this one? We don't know.
Okay.
And it's complicated analysis because you cannot find a spectral feature outside the 3.4 region to use as a proxy.
Yeah.
So that's the thing.
Okay.
And we said, okay, because these carbonates are very, very interesting. And because also we know that the presence of phyllosilicates are everywhere in Ceres. And we know that when you have organics with phyllosilicates, they protect organics from this UV irradiation. So it will be very interesting to see what is the behavior of the organics, the carbonates, and the phyllosilicate. And this is what you can see in the figure 12, just right below this one.
And there's our
This is an RGB map, but in that case, we are including the 2.7 microns band depth of the phyllosilicates.
Yes.
And we discovered something interesting.
Okay.
And it is that there are like two colors, two trends. Pernutet, Urbara, and these our two candidates are greenish, and the rest are like more blue.
Yes.
And when we represent the center depth at 3.95 of the carbonates versus the band depth, which is the figure 13, we found two groups.
Right.
Two clear groups. One group is the blue one.
Very cool.
It's the same, but just in a plot with numbers.
Mm-hmm.
It is the blue one with all these carbonates, and the carbonates of Ernutet, the candidate Urbara, and our two candidates region just isolated. Okay, so we said, wow, we have something here. It is not another carbonate. We have something interesting to explore.
Yeah.
So we put our efforts, we create this extrapolated data set that I was talking about.
Yes.
And this is what we can see in figure 16.
Okay.
Let's move again. Sorry for this.
That's okay. It's all good.
But I think it is the best way to explain to the audience.
0.4 absorption.
Yes. In figure 16, we have a 3.4 microns absorption band map.
Cool.
Okay, but with the pixel scale of the framing camera, which is something new.
Yeah.
And we can see a lot of interesting things. For example, this elongated shape of the bright spot.
Yes.
We can see newer bright spots. And even what is interesting, we have gaps without the 3.4 absorption band.
Right.
What does it mean?
Bang.
Why?
Voids.
Why only there?
Voids.
Yes, a lot of gaps. We compare the spectrum of this bright spot with the organic from NUTED,
Yes.
and also with the carbonates that are supposed to be in this region, which is what you can see in the next figure, V.
Oh,
It is just a comparison of the spectrum of our candidates
I'm with
in
you.
green, for example, in that case, together with the
Preview.
organics and the carbonates. And
Hmm.
we saw that the spectral feature of the carbonates doesn't match with the spectral feature of our candidates.
Ooh.
And our candidates are more similar to their noted organics.
No.
So as you can see, we have a lot of hints. We never confirm, but we have the spectrometric analysis, the carbonates behavior, this spectral comparison, these maps. So,
Right.
okay, there is something here. There is something here.
Right. What it is, TBD.
And
Yeah.
another, for me, it was the most shocking. It is the figure 18.
Okay.
This is not our figure. We just used from a paper from Chrome et al.
Mhm.
2018,
Yes.
where they years ago, some years ago, they defined their geologists, the geologic units on this area.
Okay.
And here we can see with these black lines, the area that we are studying with
Yeah.
our color filters.
Mm-hmm.
And our 3.4 absorption band is just in what they call the Urbara Jalode smooth material. And all these gaps
Okay.
are these yellow areas that you can see here that are just ejecta from the crater.
Cool.
So
Yeah.
it is very interesting because this Jalode Urbara smooth material is considered
Oops.
the result from the merging of deposit related to the Urbara and Jalode basin.
Yeah. Okay.
Just with just the pressing of the water ice led to the formation of these homogeneous units according to the geologists. Okay, the geologists also date this unit, and it is around 400 million years old.
Okay. Okay.
So if you have organics there, these organics will not show the 3.4 absorption band very clear because they have
So,
been there.
right. Solar radiation.
So So we said, okay, maybe they are organics, and that's the reason why we cannot see this very
Yeah,
clear.
those little
However,
bits.
we do
Right.
see
Okay.
this band clear at three bright spots.
Mhm.
Interesting. Why? Why only in this? Well, we, as I told you, this area had an intense geologic activity impact after
Right.
the impacts that formed the Jalode and Urbara basins. In fact, the Jalode and Urbana Basin are the second and third largest impacts suffered by Ceres.
Uh,
So the material that conform this geologic unit must be from a deeper
yes. Yes.
subsurface layer.
Yes.
So if they are organic, it is a confirmation of an endogenous nature.
And it's everywhere.
Yeah, so if
Everywhere.
we consider
It's triggering
that
someone.
this is what we said, okay,
Okay. Okay.
but we don't have this confirmation.
Fair.
More things. And for example, another thing, it isn't just in figure 19.
Yeah.
We studied one of these break spots, what we call BS2,
Yes.
this elongated shape, and it is not connected with a crater. The crater is in the middle, but you can
Yeah.
see this elongated shape, and you don't see a change in the slope, in the visible, in the clear filter.
Yeah.
You don't see a depression. It is just some elongated and show, shape,
Mm,
something straight. And we said, okay, if you have a secondary impact, because all this
could be.
activity, it can just uh, impact, hit the surface, and it will expose fresher material from the interior. And that's the reason why now we are seeing the 3.4 micron bands, because they are organics,
It's the only
they
one.
have been
Yeah. Yeah.
suffering
Okay.
this UV radiation, and these spots are just fresher material. So everything,
Yes. Yes.
yes, everything matches no, with this hypothesis, and that's the main result of this paper.
Beautiful.
Yes. So more or less, that's the global picture. I didn't enter in details because it is open access, so everybody can read it.
Gives you something to look
I
for.
also, yes, I also recommend going to the appendix
Ah, yes, there's a
because,
appendix.
yes, then there we put a lot of intermediate figures that we need for this analysis. So the fraction abundance map of the member from the noted scene, the abundance at different spatial resolution, uh, all the analysis that we did, the locations to get the extrapolated data set,
Cool.
coordinates, everything. So it is reproducible science. You can repeat it if you want,
Yay.
with the nice thing of science, no?
Indeed, yes, absolutely.
Yes. So
Okay.
my personal opinion is that they are organics.
Yeah,
I have no doubts, but we have to be serious in science and honest and say
we
we
don't know yet.
we cannot confirm 100%, but in my opinion, it's 99%.
Okay.
So, and it's changed everything because now this hypothesis that I told you at the beginning about the exogenous or endogenous, it is clear that if you have more organics on the surface in different locations and they are not connected,
Yes.
they must be from the subsurface. So they're endogenous,
Symbol.
and there is like a reservoir of organics in the interior of Ceres. So it is very, very cool, very nice, and mm, we feel proud of this result.
Well, you should be very proud of it. So it's very nice work. It's beautiful. Very nice. Juan, I want to thank you so much for walking us through your very awesome article on organics on Ceres. It's very nice.
Thank you for having me. Thank you.
Sure. And you kind of touched on it a couple of times as we went through. And so let me just push on it a little bit and ask where do you think we go from here given the published article? Is there more data on series coming down the pipe? Is there some theoretical work that could be done? Is there some laboratory astrophysics that could be done or on the geology or excuse me, rephrase that. Laboratory astrophysics on the volatiles that are there. There we go.
Well,
And just sort of next steps. So where do you think we go from here?
but now I am involved in other space missions in a new stage of my career. So I have no time to do all the things that I would like on series, but I would like to do that in the future.
Okay.
But what I have learned here is that you cannot say everything has been done with a data set. No? There are always new approaches, ideas, methods to develop. What I believe is that all the simpler tasks, maybe simpler is not the right
Yeah.
word, the most straightforward ones
The
have been already
low-hanging
done.
fruit.
So
The low-hanging
yeah,
fruit has been
so
picked.
we need to squeeze the data.
Right.
And
Exactly.
yeah, but I think series will be revisited in the not too distant future, perhaps with a sample return mission, I would
Yes, I
like.
was going to say yes,
The,
yes.
yes, and when we have more precise compositional data from its surface and fully understand the exact nature of the organics, we will be able to reanalyze all this existing data and to push our knowledge even further.
Cool.
Yeah.
Very cool.
So, and there are two fascinating aspects of series. One is that it is a water-rich object. You know that water can used to produce hydrogen through electrolysis,
Yes.
which is a relatively inexpensive process. And this raises the possibility that series in the future could serve as a refuel station,
Yeah,
providing
yeah,
fuel for missions
very
to
cool.
explore the other outer solar system. And
Natural
the second
testing.
is this, yes, the presence of the organics. What's below the surface? How do these organics make their way to the surface?
Yes.
No?
Uh-huh.
So it is clear that cities will continue to be a source of scientific interest and discoveries in the future. And I want to be there.
Beautiful. Beautiful. Awesome. Thank you so much, Juan.
Thank you for having me. It's my pleasure.
And that will do, everyone. And I hope this made your astronomy day or your series day just a little bit better. And we will see you on the next one. Bye bye.